Alrighty then. So we had no problems writing the negation then. So these numbers, oh gosh. Okay, let's do number 2. What kind of statement is number 2? There exists a real number x such that log x is equal to -1. What kind of statement is that? It's existential. So the negation is going to be for all real numbers x, comma, and then you have to negate the ending part. So what's the negation of log x is equal to -1? Log x is not equal to -1. Did we get at least that part? Okay, now, so the problem then is the original statement true or false? That's the problem. Are you serious? Well, is there a real number such that log of x equals -1? Well, let's just review some algebra 2. What does if there's no base written on this logarithm, what base is that? 10. And when you have it in log form, how do you change it to exponential form? This means the same thing as 10 to the -1 equals x. And is there such a number as 10 to the -1? Yeah, that's 1/10. So yeah, and is 1/10 a real number? Yeah, so it's true then, right? We forgot how to work with logarithms. You just go there and put it in exponential form. Oh my goodness. Number 6. Okay, here's the original problem. There exist natural numbers a, b, and c such that a cubed plus b cubed equals c cubed. So this is an existential statement, so to negate it, you would go for all natural numbers a, b, and c, comma, and then you have to negate that. And how do you negate gorilla equal banana? Gorilla not equal to banana. Okay, now is the original statement true or false? Can you find at least one, what do you call it, triplet of natural numbers such that a cubed plus b cubed equals c cubed? Did anybody find? Did you guys try? Did anybody find any? No, not one person found. Anyway, this is one of the most famous theorems in mathematics. Have you ever heard of Fermat's last theorem? Obviously not. Fermat was a very famous mathematician, I believe. Was it in the 1600s or the 1700s? In fact, he might have been the best mathematician in the world at that time. Anyway, we know, okay, what about, okay, instead of this, what if you had a squared plus b squared equals c squared? Can you find 3 natural numbers that satisfy this equation? Yeah, because that's the Pythagorean theorem, right? And what would that be? Can you give me at least one triplet? That's the Pythagorean theorem, people. 3, 4, 5, right? Isn't 3 squared plus 4 squared equal 5 squared? Wait, let me look. 3 squared plus 4 squared equal 5 squared. Yes! Can you find others? Yeah, 5. Okay, maybe this is a good time to review your basic Pythagorean triples. 5, 12, 13, 8, 15. Oh my goodness, 17, 7, 24, 25. Come on, when you come out of kindergarten, those are the 4 basic ones. Are there more though? Yeah, there's an infinite number of them, right? But these are the 4 basic ones, right? I'm sure when you took trigonometry, your teacher told you to remember these, right? When you draw the triangles. Okay, but what happens when the power gets bigger? Instead of 2, it's 3 or 4 or 5. Well, there was a very famous problem back then, and they said, well, if you had a to the n plus b to the n equals c to the n, n. Because everybody knew when n was 2, there was an infinite number of solutions, but what happens when n is 3 or 4 or 5 or bigger? So nobody could find any solutions, so if you can't find any solutions, does that automatically mean there's none? No, because just because you couldn't find it, that doesn't mean it's not there, right? It's just that you couldn't find it. So you have to, in order to solve this problem, you have to do a mathematical proof. And then somebody offered money, because this problem was so famous. Somebody said, I think it was somebody in Germany said, if somebody can solve this problem, I'm going to give you all this money. I forget what it was. But nobody could find a proof to do it. And then Fermat, since he was the world's best mathematician at the time, he said, oh, I could do that. It's kind of easy for me. But then the problem was, he really didn't put a formal proof. He just kind of scribbled in a book. In fact, he was sitting, I think, in his house, and he had a book, and then in the margin of the book he wrote, I have a wonderful proof for this, but the margin of this book will not hold it, or something. And then he died shortly after that. So nobody really knew if he actually proved it. So what he was trying to prove was that if this number n is 3 or bigger, then there are no solutions. And then throughout the years, all the way until, when did somebody finally prove it? In 1991. Somebody actually proved it. You ever heard of Andrew Wiles? He's still alive. He's at Princeton University. When he was a little kid, he heard about the problem, and then his goal in life was to solve this problem from when he was a little kid. And then in 1991, he thought he had a proof that actually solved this problem, but then of course, when you submit a proof, mathematicians have to check it to see if it's correct, yeah? So mathematicians checked it, and then they found out that there were some holes in the proof. And then so he tried to fix it, but he couldn't. And then he became very depressed, and then he didn't do anything for a while. And then all of a sudden, I think he was walking on a river or something, in 1993, he had an epiphany, and he figured out how to fix the proof, and then that was it. So now he is credited with solving Fermat's last theorem. So, yes, this original statement is false. Now we know because of Fermat's last theorem. You cannot find 3 natural numbers that satisfy, as long as if the power is 3 or bigger, you can't find any. That's Fermat's last theorem. 19 people, did you know about it? And where did you learn it?
Oh, you were talking about it again last year.
And then you remembered it. Yeah. When did you walk in? Okay, whatever. Let's move on. Number 9. Okay, we gotta erase because we're videotaping, so we only can use this side of the board. Number 9. What kind of statement is this? Every even number greater. Do I have to write the negation? Or you guys can do that part. When you see the word every, that's like for all, right? So that's universal, right? So the negation is going to be existential. So every even number, so the problem is the true or false part, is that it? You guys couldn't figure out by looking at the answers on the bottom. Every even number greater than 2 is equal to the sum of 2 prime numbers. Now this is not a theorem. You guys know the difference between a conjecture and a theorem? A conjecture is a statement that somebody just says, but it hasn't been proven yet, okay? So this is a conjecture. This is called the Goldbach Conjecture. This is like the most famous problem now that hasn't been solved. So if you could actually solve this problem, you would be pretty much the most famous mathematician on the face of the earth. Right here. Now think about it. Every even number greater than 2, so you think 4, can that be written as the sum of 2 prime numbers? Yeah, 2 plus 2. Are some of you thinking 1 plus 3? I hope not, because 1 is not a prime number. What about 6? Can 6 be written as the sum of 2 prime numbers? Yeah, 3 plus 3. What about 8? Can that be written as the sum of 2 prime numbers? Okay, thank you. What about 10? Oh, you're going to, okay, I was going 5 and 5, but you want to go 3 plus 7, okay. So that proves it then. No, just because you prove it for the first 4, that doesn't mean it works all the way off for all even numbers. Okay? Anyway, this is a conjecture that has never been proven, so that's why there's a question mark there. We don't know. That's a trick question. Sometimes I like to put that in on the test. We don't know. Anyway, when I put that Goldbach conjecture there, you guys didn't like punch it in on Google or something, what the Goldbach conjecture is? Some people, what do you think that question mark meant?
That was a typo.
And so you didn't know if it meant no or yes, or true or false. Oh my gosh.
Question mark.
Okay, number 10. For all real numbers x, comma, there exists a real number y such that x times y equal 1. Now what kind of statement is this? No, just look at the first symbol. For all. This is a universal statement. Now remember, now did you guys have problems negating this? I think some of you did, yeah? See, this is how the kind of problem we put on so that you gotta think. For all box, comma, triangle. Okay? How do you negate a universal statement? You just follow the form. There exists box such that not triangle. Now this is the triangle right here. Now what is the triangle? What kind of statement is that? Yeah, because the ones I gave you before were just simple ones, but now it's an existential statement. So you have to negate that. How do you negate an existential statement? It's a universal. So how do you negate this? For all real numbers y, comma. So inside the triangle, you have like, there exists box such that triangle. It's like, embedded. So how do you negate that? For all box, comma, not triangle. So x times y is not equal to 1. You guys know what I'm talking about? Okay, now is the original statement true or false? For all real numbers x, you can find another real number y such that x times y equal 1. So no matter what real number you think of, you can so here, think of a real number, 3. No matter what real number you think of, there's always another real number so that when you multiply them, you get 1. 3 times what will give you 1? 1/3. Any real number. How about 4/5? Can I multiply 4/5 by something and get 1? So any real number you think of, you can find another real number so that when you multiply them together, you get 1. No, because look at the answer on the bottom. What about 0? What do I multiply 0 by to get 1? 1 over 0, because then you cancel out the zeros. No, this is undefined. And that's the counterexample right there. So that's why the original statement is false. Yeah, 1 over 0. Okay, so does that answer all the questions for the first part? Okay, then what about the truth table? I thought somebody had a question. Oh, I answered it already.
Yeah, yes.
Okay, now what did we learn from these truth tables? What did we learn? In fact, 11 and 12, didn't I do that as an example? I guess it's so lucky. Okay, so 11 and 12 had exactly the same truth table. So if two statements have exactly the same truth table, what do we say? They are logically equivalent. And then the next two, not P and Q, is logically equivalent to not P or not Q. These two are called De Morgan's law. Named after the logician. I told you guys last time. Augustus De Morgan. What's going to happen on the semester exam when you have to match the first name with the last name and then with what the theorem that the mathematician is famous for? What's going to happen?
Why?
Pain. Pain, that's what's going to happen. Augustus De Morgan. Oh boy. Okay, and then number 15 and 16, did you notice anything? Yeah, they have the same truth table. So this truth table came out exactly the same as this one. So that means they are logically equivalent. Now, I don't think we have a name for this one, but doesn't this one also remind you of the distributive property? Look, you have P or, and then you have an and statement here. So you can kind of distribute the P or. So you get P or Q, and then P or R. Okay, now we haven't proved it yet, but you can probably guess that, and notice I said yet, yeah? You can probably guess that what would this be logically equivalent to? I mean, just by looking at the form. What would you guess? Oh my goodness, people, look. P and Q or P and R. Now you can probably guess they're logically equivalent, but can you say they are? Okay, let me ask you this on Tuesday's quiz. What if I were to ask you, prove that this is logically equivalent to that? What would you do? You make a truth table for this, you make a truth table for that, and then you show that they're exactly the same. That's how you prove it. Okay. That was pretty painless. Oh, wait a minute. What about number 3? Everybody knows why number 3 is false? Because I don't see it up there. So this is the only year, this is the first year in the history of pre-calculus honors where everybody knows why that's false then. Okay, then we're not going to have high scores on the quiz and test. Nobody wants to ask? Okay, there you go. Why do I? You guys supposed to put, remember I told you guys, if you don't know something, write it up there. You guys are killing me. Okay, for all real numbers x, the square root of x squared is equal to x. This is false. You want me to give you an example? That proves that this is false. Is the square root of -3 squared equal to -3? -3 is a real number. Is the square root of 9 equal to -3? I don't think so. Okay, what would I have to change here to make it true? Okay, I'll tell you, this is the problem right here. Why, do you guys really think that the square root of x squared is equal to x? Because if you do, that's not good. What should it be? It's printed in it's printed in pretty much every algebra and pre-calculus algebra 2 book ever printed. What should it be? The square root of x squared is not equal to x. It's equal to its absolute value of x. That's what it should be. Now some of you are thinking, shouldn't it be plus or minus x? No, it is not plus or minus x. It's the absolute value of x. There's a big difference between the two. So now, if I put the absolute value on, is that true? Well, maybe, you know what, maybe you guys just don't know stuff. Okay, let's go back to algebra 1. Let me ask you this. What's the square root of 4? Oh, there you go. No, it's 2. It's 2. Who said plus or minus 2? Okay, let me show you something. A lot of oh gosh. Okay, how would you solve this equation, x squared equal 4? You square root both sides, right? You square root both sides. Okay, now, what is the square root of x squared? We just learned it. It's the absolute value of x. What's the square root of 4? It is 2. It is not plus or minus 2. It's 2. So, solving for x, the absolute value of what number will give you 2? Plus or minus 2. But see, the thing is, a lot of teachers, you know, when they do algebra on the board, they skip this step. So that's why a lot of students think the square root of x squared is x, and the square root of 4 is plus or minus 2, but that's 2 mistakes right there. That's because they leave out the step. That plus or minus comes from the absolute value. I'm glad you asked it. Oh boy. We're in a heap of trouble. Okay, what are we learning today? Oh, we got to do some more truth tables, and we got some networks to learn about. Okay, so this should be pretty easy. Okay, yesterday we learned 3 truth tables, right? Or was it the other day? Whatever. The last lesson we learned 3 truth tables. Of course, the simplest one is the negation one. I'm not going to even do the negation one. And then what about this? If you have 2 statements, P and Q, there's 4 possibilities, right? True, true, false, false. True, false, true, false. Okay, then we learn the OR statement, P or Q. Now, what's another way of saying this? P or Q. What's another way of saying this? Jason.
Not P.
No. That, exactly. If you saw that, how would you read it? One way is P or Q, right? But what's the more formal way? The disjunction of P and Q. How do you know that? It's in the notes. Now what's the truth table for P or Q? True, 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 false. You guys have that memorized yet? Or you just go, oh, it's true when at least one of them is true. Whatever, it's the same thing. Okay? Then we learned and, P and Q. What's the formal way of saying this? The copy?
P conjunction.
No, the conjunction of P and Q. Okay, so Mr. Park, do we have to know that? No, you don't have to know anything in this class. It's optional. True, false, false, false. Boy, can you keep that straight? This junction is or, conjunction is and. Look here, let me show you a shortcut to help you remember. This junction is or. Conjunction is and. I just made it up now. Or you can pick whatever you want. Pick up whatever you want. Okay, now we have to only learn 2 more truth tables today. And then we're going to derive all the other ones just from these basic ones here. So the first one is this. This is called the conditional statement. Okay, now look at your notes. There's lots of ways of saying this. The most common way is if P, then Q. If P, then Q. Now, where have you heard conditional statements before?
Latin.
Latin, like what?
Like if, then, or should, would.
Yeah, but can you give me an example like in a sentence? If you don't do your homework, I'm going to kick you out of class.
Yeah.
And only in Latin class you hear that.
We did Chinese too.
No, I was hoping you would say geometry. In fact, when you read mathematics books, anytime you're given a theorem, it's probably going to be a conditional statement. Okay, let's go back to geometry. If 2 parallel lines are cut by a third line, then the alternate interior angles are congruent. That's called a conditional statement. Does that sound familiar? Oh my goodness. So yeah, so when you read math books, a theorem will probably be a conditional statement. Now that's not the only way to say it. You better look at your notes now. If P, then Q. Another common way would be P implies Q. Q if P. P is a sufficient condition for Q. Q is a necessary condition for P. All of those mean that. They mean the same thing. Now, if you're lucky, I won't give, the only one I'll give you is if P then Q or P implies Q, but you just never know. You know what the most confusing one for students is? P is a sufficient condition for Q. And then Q is a necessary condition for P. Anyway, let that percolate. Now, what is the truth table for that? You know what, I'm just going to tell you. It's true, false, true, true. Okay, let's look for a pattern. Now remember, these are the training wheels right here, right? These are the components right there. So notice that a conditional statement, the only time a conditional statement is false, right, is when? Right here. When the first one is true and the second one is false. That's the only time it's false. What the heck is that? Is that a phone? Oh, you're looking guilty there.
I don't even have that ringtone.
Whose phone is it? I'm going to answer it right now. Let me answer it right now. It came from here. Oh, you guys are good at pretend like you don't know. Because you're playing the game. The only time a conditional statement is false is when the first one is true and the second one is false. And by the way, when you have a conditional statement, what is the first one called? It's in the notes, people. Here's a conditional statement.
Modus.
No, you can at least look at the right part of the notes. This thing here is called the... No. It rhymes with my hypothesis. How do you know? Because he's looking at the notes.
I am too.
But you're looking at the wrong part. The second part of a conditional statement is called the conclusion. So the only time, you guys have the notes right there, you guys didn't get it. The only time a conditional, oh, I'm trying to compose myself here. The only time a conditional statement is false is when the hypothesis is true and the conclusion is false. Now, let me give you an example to help you remember this. Okay, what if I make this statement to you? If you do your homework, then I will pay you $5. Okay? What would happen if you did your homework and then I paid you $5? Am I a liar? No. What if you did your homework and I didn't pay you $5? Am I a liar? Yeah, see, false. What if you didn't do your homework and then I paid you $5? Am I a liar? No, I'm just stupid, right? I'm not a liar, I'm just stupid. What if you didn't do your homework and I didn't pay you $5? Am I a liar? No, so the only time I lied, right? Doesn't that make sense? You did your homework and then I didn't pay you $5. So that's the only time a conditional statement is false, right there. Okay, then the next one is, now notice how the arrow goes from here to here, right? Because it's if P, then Q. The arrow goes that way, but what would happen if the arrow goes both directions? We call this is called a conditional statement. This is called biconditional. Now, if you read math books and you've been doing it since, I don't know, when have you been reading math books? Since 5th grade? Okay? The biconditional statement, the most common way of saying this would be P if and only if Q. Have you ever heard that phrase before? If and only if? That's biconditional. That's why, so this means basically if P then Q, but it also means if Q then P. You can go either direction. Normally you see biconditional statements in definitions in mathematics. Okay, let me think of one. A triangle is isosceles if and only if two sides are congruent. Okay, let's break that down. That means you can go both directions. If a triangle is isosceles, then two sides are congruent. If two sides of a triangle are congruent, then the triangle is isosceles. See how you can go both directions? But that's the definition of an isosceles triangle right there. Okay, so anyway, another way of saying this is P is a sufficient and necessary condition for Q. Anyway, this is the truth table. I'll just tell you. True, false, false, true. Now let's analyze that. When will the biconditional statement be true? Here and here. Look, what do you notice? When both of them are the same. So when both of the components are the same, the biconditional is true. And when is the biconditional statement false? Look at this. When they're different. That's the easiest way to remember. So when you do your homework tonight, again, you're going to be making truth tables. I think the first several problems you're going to, but then you got to learn from it. Okay, I'm going to do the one of the more basic ones for you. Let's make a truth table for not P or Q. This is one of your homework problems. I'm just doing it for you right now. Okay, let's make a truth table for that. Okay, here's Q. Q is true, false. Let's see if we can do this in our head now, because we have experience now. Okay, not P. If P is true, true, false, false, right? Therefore, what would not P be? Okay, you know what? I don't think we can do it. So let's just write false, false, true, true. And then Q is true, false, true, false, right? Now, or. When is the or statement true? When at least one of them is true. Is at least one of them true? Yes. Is at least one of them true? Is at least, no, that's a no, boo. Is at least one of them true? Yes. Is at least one of them true? Yes. So this column represents that statement. Now, what do you notice about it? You got to learn something from it. That's the same as the conditional statement. Look, true, false, true, 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 false, true, true. So what did we just learn from this problem? Yeah, P implies Q is logically equivalent to not P or Q. That's super important. Anyway, it's in your notes. Because in your notes, if you look, there's a section that says important equivalences. That's one of them right there. I'll tell you right now, you cannot pass this test unless you know this right there. Okay, let's just do one more for funsies then. Not Q implies not P. Make a truth table for this. I'm doing another one of your homework problems. Okay, well, Q is true, false, so what is not Q? False, true, false, true. P P is true, true, false, false, so what is not P gonna be? False, false, true, true, okay? Now, we're doing conditional. Now, when you have a conditional statement, if the first one is false and the second one is false, what?
True.
It's true. Remember, the only time a conditional statement is false is when the first one is true and the second one is false, right here. That's the only time it's false. All other cases, it's true. Oh, what do you notice about that? Hey, that's the same as this one and this one. So they're all logically equivalent, all three of them. So what did we learn from this? Look at these two. This is what we learned in geometry. You should have learned this, but you guys probably forgot. If you have a conditional statement, P implies Q, what is this? Not Q implies not P. That's called something. That's called the contrapositive. Does that word sound familiar? Some of you are nodding. Some of you, what the heck are you talking about? Okay, let's go back to geometry. A conditional statement is what? P implies Q. Now, when you have a conditional statement, you can form these other statements. One is called a contrapositive. This is all in your notes, people. And what's the contrapositive of gorilla implies banana? Not banana implies not gorilla. What about the converse? If the original conditional statement is P implies Q, what is the converse of that? Are you looking at your notes? Q implies P, and then what is the inverse? There's only one other possibility here, people. Not P implies not Q. So if you are given a conditional statement, you can form these three other statements. Do these words sound familiar? Converse, inverse, contrapositive. But what did we just learn here? Any conditional statement is going to be logically equivalent to its contrapositive. Hey, wait a minute. Didn't we learn that in summer school if you were in my class? Paige? Yes. Now you got to know it. That came up on a PSAT several years ago. Oh my goodness. Okay, so again, when you do tonight's homework, look for things that are logically equivalent. Oh my gosh, look at the time. I keep thinking we're going to finish early. We don't. Okay, last thing today. Look at the bottom part of tonight's homework. What the heck is that? Now, is there like a logical, a real life application of logic? Yes, electricity. Right, because remember the logic we're studying, there's only two possibilities, either true or false. But isn't that like electricity? Like if you have a wire, either it's flowing or it's not flowing, right? You guys do computers? Some of you do computers? Mason? I thought I saw you in the computer programming class in the summer.
No.
So you guys didn't learn about binary number system?
Didn't pay attention.
Oh gosh. Okay, you have a wire. Either current is flowing or it's not flowing. So if it's flowing, or think of it as on, we call that 1, which is like true. And if it's not flowing or off, we call that 0. It has exactly two states, either on or off. It's like true or false, or flowing or not flowing. You guys get it? So that's perfectly, this is logic right here. So what we can do is we can build these networks. We can call, and if you go and study engineering in college, if you can remember what I'm teaching you right now in logic, you're going to be way ahead of everybody else. Electrical engineering is basically logic. And what about law? When you go, some of you thinking of becoming lawyers? I bet some of you are. You have to take a test to get into law school. You know what the test is called? The LSAT. And you know what's the most important thing on the LSAT? Logic. So many of my students have come back and they say, Mr. Park, thank you for teaching me logic, because now the LSAT was so easy. Because if you know that the contrapositive is the same as the conditional, you can solve so many problems on there. They said logic was invaluable. Okay, anyway, so basically today we got to learn how to draw networks. Now there are 3 gates. They're called gates. Okay. The first one is this. This is the not gate. Basically, it works like negation. Okay, so this is how it works. If the input is coming in as a 1, what do you think the output's going to be? 0, because it negates it. It changes the sign. Not really the sign. What if the input is a 0? Then what do you think the output's gonna be? It negates it, people. It's gonna be 1, it just changes it. It changes the state. Okay? The next one is the AND gate. Now, you have to have 2 inputs to this. This is what the AND gate looks like, AND. Okay? And it works just like the AND statement. Okay? So, when is the AND statement true? When both of them are true. So, if this is a 1 and this is a 1, what do you think the output's going to be? 1 is true, 0 is false, people. If this is true, if this is true, what do you think the output's going to be? True, it's going to be a 1. But what if this one's a 1 and this one's a 0? What do you think the output's going to be? Yeah, because only one of them is true. 1 is true, 0 is false. Okay, and the last one is the OR gate. You have two inputs. It looks like this. These are all standard electrical engineering symbols now. It works just like the OR statement. So if this is a 0 and this is a 1, what do you think the output's going to be? If you have an OR statement and 1 is false and 1 is true, what is it? It's true. There you go. So tonight's homework, you're going to have a network. Okay, let's just make up one for now. Okay, here's P, here's Q. Okay, let's make up something. Woo! Woo! So we negate this one. Okay, and then we put these two together with OR. And then over here, something branches out. It comes over here. And then it's going to go with this one here. And it's going to go into AND. And then it's going to get negated. And then over here, this one, this is how you jump over a wire. And negate it, and then it comes with this one, and then these two goes with OR. Okay, good enough. This is a network. We call this a network. Okay, so one of the problems tonight is you're going to see a network like this, and you have to symbolize it. Okay, how do you symbolize this? Well, first, if you have P here, what happens to P? It gets negated. Then what is this symbol here? This is OR. It gets ORed with what? What does it get? What's the 2 inputs going into the OR here? Q. Okay? So when it comes out, that's this. But then this output goes into this, which is an AND, and what does it get ANDed with? What's this thing here? Look, go back. Look. That's P. But then it comes out of here and it gets negated. So all of that gets negated. And then this comes out, and what is this? It gets ORed with what? Go back here. What is it? What the heck is this? No, not Q. Not Q. And there you go. That's how you symbolize that network right there.
We don't need to make a truth table.
Wait, let me look at the directions. No. If it says make a truth table, then you make a truth table. If it doesn't say make a truth table, you don't make a truth table. Okay, now, and then the next question is going to be, what if the input here was a 1 and that one is a 0? What is the output over here going to be? Well, let's just go. Okay, here, P is 1, then it gets negated, so what is it going to come out as? A 0. Now, Q is 0. So both of these are going in as zeros. This is OR. So what is it? If both are false, OR statement. False. Okay? So it's going into AND here. But what is it getting ANDed with P? Well, P is 1. So this is like 1 and 0. So you have an AND statement. If one of them is true and one of them is false, it's false. But then it gets negated. 1. Now, if you're smart, you really don't even care what the other one is because you know it's going to be 1, right? Because an OR statement, if one of them is true, then it doesn't really matter what the other one is, right? Just at least one of them is true, right? So the output's going to be 1. So that's the beginning of electrical engineering right there. Now, you want me to give you a preview for the test?
Yeah.
Okay, I'll tell you. This has always been the last problem on the test. Okay, you have 2 inputs, P and Q, like this. And you can start thinking about this. So P, it's always going to be the same. True, true, false, false, true, false, true, false. Okay? Design me a network. Design me a network that produces the following output. And so what I do is I just make up something here. Okay, so here, I'll just do one for you. How about 0, 1, 0, 0? Okay, this is really easy. You probably wouldn't get this on the test. Okay, we got 1 minute, 2 minutes to do this. Now, this is the kind of thinking that you should have. A, That's the negation of something I know. This is like false, true, false, false. This is the negation of true, false, true, true. And where have I seen true, false, true, true before? You just learned it today, people. That's the conditional statement. You guys know what I'm talking about? Hey, so this is simply the negation of P implies Q. Yeah, but the problem is, you only have symbols for not and or. There is no symbol for conditional. So what do? You gotta know something. What did we learn today? About 10 minutes ago. The conditional statement P implies Q is logically equivalent to not P or Q. See, that's what I mean. If you don't know that, then you can't do problems. Woohoo! And then now, can you draw a network for that? Yeah, now easy. So you have P, Q. Let's do this quickly. So not P gets knotted, go, and then both of them get ORed, what? And then the whole thing gets negated. And there. And then you're done. That's the last problem on the test. Except I'm not gonna see this part here. See, this is easy. I'm not gonna give you an easy one. It's gonna be something more challenging, as you will find out. Okay, we're done. Whoa, what? Are we ever gonna finish early?